Hello there, welcome to this video. This is lesson 4 of our first unit on polynomial functions, and today we're going to talk about key characteristics of a polynomial function based upon a leading term of a polynomial function. Our learning target, we're going to determine the key characteristics of a polynomial function, and you know you're successful if you can identify the leading term and use that leading term to describe some key features of a polynomial function. So let's get into a definition of a polynomial function. A function of the form p of x equals a sub n, where a sub n is some number or some coefficient, times x to the power of n, again where n is some power, plus another term here. So some coefficient with another variable x with a term power that's one less than the one before, and so on and so forth. I can have as many terms as I want, okay, but the whole idea here is that a polynomial function is in standard form. The bigger powers first, and we get all the way down to eventually, you don't have to have, but we have a linear term, x to the first, and then finally a constant. Okay, so here's an example of a polynomial function. Here we have f of x equals x to the fourth plus 2x cubed minus 4x squared minus x plus 2. That's a polynomial function. It can be as simple as something like this. G of x equals, let's say, 2x squared plus 5. That's a polynomial function. It can be something also as simple as h of x equals negative 3x cubed. A monomial. That's also a polynomial function. The idea here is that you have a collection of terms that have a variable in them with powers. Okay? So, a leading term. The leading term of a polynomial function is the term with the highest degree. The leading term is the term with the highest degree or highest exponent of an independent variable. So in these examples up here, if your polynomial function's in standard form, which it's not always, it's going to be the first term. So I have x to the fourth. That's my leading term. I have negative x cubed. Well, that's the only term. And then the next one, 2x squared. So those are the powerful, most strongest terms in our polynomial function. So those are the leading terms. Now the leading coefficient is just what it says it is. It is the coefficient of the leading term. So in our first example, f here, the leading coefficient is 1. For g, the leading coefficient is 2. And for h, the leading coefficient is negative 3. What does the leading term tell us? It's very, very useful when analyzing polynomial functions. It can go ahead and it can tell us the number of zeros that we have, or x-intercepts, the maximum number, okay, of real zeros. Number 2, it can tell us the maximum number of turning points, or extrema. Extrema, also known as maximums and minimums, extrema. And it will tell us the nature of the behavior, which is probably the most common and practical application in the AP calculus exam. Let's go ahead and let's look at turning points. Turning points. Well, actually, first of all, I want to back up something. Something they didn't include here. Please add this is extrema. So the maximum number of real zeros will be based upon the degree. So whatever degree your leading term is, that's going to give you your maximum number of real zeros. Can't be any more. Could be less because we could have some imaginary zeros, or we could have what's called multiplicity, where the zeros repeat, but that will be your maximum number. Now, turning points. A turning point of a polynomial function are, again, the local maximums and minimums, and this is where a function changes from increasing to decreasing or vice versa. Now, how we use the degree of the leading term in order to determine the number of turning points is we go ahead and we subtract 1 from whatever that degree is. So let's say my degree is 5. The maximum number of turning points I will have is 4. Very simple. Minus 1. And finally, end behavior. We can determine end behavior from the leading term. We can determine, based upon the powers of that leading term, what's going to happen to my function as x goes all the way to positive infinity and as x goes all the way to negative infinity. So that's where I want to go ahead and start, because the other two characteristics are very simple. But I want to go ahead and talk about n behavior. So I'm going to split this notes page into quadrants, into 4 quadrants, looking like this. Okay, and what I want to go ahead and cover first is probably our most foundational is even degree, an even degree. What if I have a function that has an even degree? In a classic example, something like x squared. So let me go ahead and draw that in green over here. So y equals x squared. That's a parabola. It doesn't look something like this. Just very simple. What do you notice about those n behaviors? They're both going up. Okay, let's go ahead and look at y equals x to the 4th, which is kind of the example given in this example. We have f of x equals 3x to the 4th as our leading term. Notice the n behaviors, again, are going up. Okay, what happens, so they're both going up, what happens if I slap a negative in front of that? If I add a value that has a negative, so y equals negative x squared. Well, that's going to cause a vertical reflection, and now our graph is facing down. And notice in this given example, again, the negative 3x to the 4th, notice how our function is now going down. Okay? The moral of the story here that I want you to pick up on is that for an even degree, if my power, my leading term on the power is even, my n behaviors are going to be going in the same exact direction. Now with odd, I want you to think opposite. The n behaviors are opposite. So notice here I have 2x cubed. Okay, my right n behavior is going up and my left n behavior is going down. Well, what happens if I add a negative? Again, that's going to cause a reflection and my right side goes down and my left side goes up. Okay, so think even, I want you to write same. You're going to have the same exact n behavior. Odd, I want you to think opposite. You will have the opposite n behavior. Now, how do I know which side goes where? Well, it depends upon the positive leading coefficient and the negative leading coefficient. And what I want you to pick up on is that if my leading term is negative, notice I have a negative here and a negative here, the right side is going to go down. That's what we will determine first. Is it positive or is it negative? If it's negative, right side goes down. So notice here our n behavior, again in limit notation, the limit of f of x as x goes to positive infinity. My right side's going down, and that's true for both of the even and odds. So what does the left do? Well, we're going back to what we talked about before. If it's even, the left side's going to match. Okay, so if right's going down and it's even, the left side's going to go down. What if the right side's going down and it's odd? Well, the left does the opposite. Left will go up. Okay, and vice versa. If the positive coefficient is positive, right side's going up. Okay, so I'll go ahead and talk through these problems that we'll see. I'll teach you some annotation tools, and we'll go ahead and answer some of these questions. All right, example number 1. They say answer the following questions for the polynomial function f of x equals 3x squared plus 5x cubed plus 8x minus 1. The first thing you should always go ahead and check is your function in standard form? And this one was not. We had our second term being the leading term. Our leading term is 5x cubed, and the degree of this, the degree is 3, and my leading coefficient, I'll just write coefficient here, was 5. Okay, so make sure that you organize it, or you can at least identify the leading term. Don't always take it for granted that it's the first term. So the x-intercepts, how many x-intercepts does my graph have? Well, my degree is 3. So, I mean, at max, it's going to have 3. I'll put 3 here. And then how many turning points? Well, you're going to take the degree. You're going to take your degree and you're going to subtract 1. So that is 2. Maximum 2 turning points. Okay, maybe I'll put the degree. This is just your degree. 3. End behavior, most practical application of this. Here's what you're going to do. You're going to go ahead and you're going to look at the leading coefficient. And the first thing that you're going to do is you're going to answer the question, is it positive or is it negative? And so looking at this, 5, that is positive. Positive. Okay? The second thing that you're going, so what does that mean? If it's positive, what does that mean? Well, that means that my right side is going to go up. Right side will go up if it's positive. Okay? All right, second, what do I check next? Is it even or is it odd? And here, this is odd. What does that mean? What does that mean? Well, that means that the left side, if it's odd, it's going to do the opposite. So instead of going up, the left side will go down. So this is your end behavior. Right side's going up, left side's going down. Very, very simple. We just now need to translate that into mathematics and using limit notation. So question E, what is the end behavior of f as x increases without bound? Increases without bound. Well, what they're asking you therefore is the right end behavior, x increasing without bound. So my limit notation, the limit of the function, which is called f, as x approaches positive infinity. That's increasing without bound. I'm going to positive infinity. Okay, and we said the right side's doing what? Right side's going up because it's positive. So my y values are going to increase to positive infinity. F, what is the end behavior of f as x decreases without bound? Okay, so I want the limit of f of x as x decreases without bound. Decreases without bound. That's the left end behavior. We're going to negative infinity. Okay, and we said that the left side's doing the opposite, which is going down. Hopefully that makes sense. Remember, first question, is it positive or is it negative? That's going to tell you the right side. Second question, even or odd? That will tell you what the left side does. Here's a practice problem. Please pause me, try this, and then I'll go over the example or the answers here in a second. Okay, hopefully you paused it. The leading term of this polynomial f here is negative 2x to the power of 5. The leading degree is 5, and the coefficient is negative 2. Okay, the intercepts, it's going to match the degree. That's 5. 5 intercepts max. Could be less. How many turning points does the graph have? Maximum, it's going to be one less than 5, which is 4. And then what is the end behavior of f as the limit of f decreases without bound? So this is x goes to negative infinity. Decreases without bound means the left side. Okay, well, let me go back, look up here at my leading term. My coefficient is negative. My coefficient's negative, that means the right side's going down. And the degree is odd, so left side does the opposite. So my left side, it's going up. This is going to be a positive infinity. Did you get it? Yes. Good job. Okay, next. What is the limit of f of x as x approaches positive infinity now? Well, the right side we just said, it's going down. Okay, hopefully you got that right. Last example that I have for you guys. We now have a polynomial function g, but this is in factored form. Please make a note. This is factored form. Factored form is pretty awesome. It helps us find zeros and solve things. But right now, I really, to answer these questions, I want to know what the leading term is. So how I find this leading term is I'm going to take all of the leading terms and I'm going to multiply them together. Okay, so I have 2x. And notice how it's squared. Do you see how it's squared? That means I have it twice. 2x times 2x. And then I have another x. And then the last term is a negative x. Negative x. Okay, I'm going to multiply all these together. That would put it in standard form. So what I get is 2x times 2x, 4x squared, times x, 4x cubed, times negative x. That gives me negative 4x to the power of 4. So my leading term, negative 4x to the 4th. Again, my degree here is going to be a positive 4, and the leading coefficient is negative 4. Intercepts will match the degree. Okay, so again, 4. Turning points is 1 less, 3. And then my end behavior is again based upon that leading coefficient. So my leading coefficient is negative. So right side's going down. Again, we look at this first. Positive or negative? Right side's going down. Secondly, even or odd. Okay, this one's even, so that means the left side matches. That one's going to go down. So let's go ahead and answer E and F. What is the end behavior of G as x decreases without bound? Okay, they're asking us in mathematical language, what's the left end behavior? So the limit of G of x as x decreases without bound is going to be equal to negative infinity. Left side goes down. Next one. What is the end behavior of G as x increases without bound? Okay, this is the right side. The limit of G as x approaches a positive infinity, that's the right side, okay, is also going down. There you have it. Okay, here is the last practice problem. I want you to please pause this and try this. And I want you to pause first because I want you to determine what's the leading term of d of x. Please verify, because if you get this wrong and you try everything, it's going to throw it off. So d of x, ready, set, go. Okay, hopefully you paused it. Here's how you find your leading term. You're going to take the x here. You have x plus 4 twice. So that's x times x. You got 2 of them. And then we have a 3x. And then we have x squared. Okay, so if you multiply this all together, I believe that's 6. 1, 2, 3, 4, 6. Yeah, 3x to the power 6. Okay, so your degree is 6. That means you have 6 x-intercepts and 5 turning points. And your coefficient is a positive 3. So what does that mean? Well, it's positive. Right side's going to go up. Since it's even, left side's going to match. So there's your end behavior. Okay, so our limit statements. The limit of d of x as x approaches positive infinity, this is the right side because it increases without bound, is going to positive infinity. And for f, the limit of d of x as x approaches negative infinity is also going to positive infinity. All right, hopefully in this video you learned how to analyze the leading term of a polynomial function, determine how many zeros and turning points it has, and its end behavior. Go ahead, please thumbs up, like, subscribe. I'll catch you in the next awesome math video. See you later.